Factoring polynomials. So we've done some factoring in the past, but the only factoring that we've done is with an exponent of 2. Well, polynomials can have a higher exponent than just a 2. They can have a 3 or a 4, a 6. So we need to kind of delve a little further into factoring. And so to help us with this, we have this flow chart here. So this tells you kind of the process your mind should be going through when you factor. So step 1 should always be looking for a greatest common factor to take out and make your numbers simpler if possible. Then count how many terms you have in the leftover polynomial. If you have 2 terms, follow these 2 steps. If you have 3 terms, follow this process. And if you have 4 terms, follow this process. So we've kind of done 3 terms in the past. We have done the AC method. That's when you multiply the A and the C together and which numbers multiply to that but add to B. We've done that. Let's talk about what happens if you only have 2 terms. That's new. And that's this piece down here at the bottom. So these are called special cases of polynomials. There's 3 kinds of special cases. There's difference of squares, sum of cubes, and difference of cubes. And each one has a formula that you can follow. These formulas are not, you do not have to memorize these formulas. We will be giving them to you. And so just recognizing when and how to use them is what's important. And so for difference of squares, we know that it's a difference of squares because first of all, difference means subtraction. And squares means that your 2 terms are both perfect squares. So like a 9, a 16, a 1, an 81, something like that. And so to find out what values are going for A, we're going to take the square root of A squared. And it should be a nice whole number. Then to figure out what values are for B, we're going to take this guy and we're going to take the square root of B squared. And then we're going to place those values that we get, this number and this number, into the correct places in my formula. So let's look at an example. So for example 1, always look for a GCF first. So 9x squared and negative 25 do not have a common number that I can divide out. So then we see, well, there's 2 terms and there's a subtraction. So possibly this could be difference of squares. And so we check. This guy here should be a squared if it is difference of squares. And so to find A, I should be able to easily take the square root of 9x squared. Square root of 9 is a 3, square root of x squared is x. So far, this follows the difference of squares. 25 should be b squared, and so to find b, I should be able to take the square root of 25, which is a 5. So this is a definite difference of squares. So what we're going to do is we're going to use this pattern, a plus b times a minus b, to factor this quickly. So we have 2 factors. The a's are going to go in the front, so 3x go in the front where the a's are. B, which is 5, will go in the back. And then we put 1 positive and 1 negative. And this is the difference of squares factoring pattern for 9x squared minus 25. If you wanted to check, you could simply multiply this back out and you should end up back at 9x squared minus 25. So for example 2, try to divide out a common factor first. 81x to the 4th and negative 8 or negative x squared, I can divide both of those by x squared. So this x squared is the GCF. And so we're going to pull x squared to the side, and then we have 81x squared left over minus anything divided by itself gives me a 1. So now what we're going to do is we're going to use difference of squares to factor this middle piece here. Pause the video and try to get the difference of squares factorization for 81x squared minus 1. And here's what you should have had for example number 2. Don't forget to pull out the GCF way down to the bottom as well. This guy's just going to tag along all the way through. Now let's look at sum of cubes. So the difference between difference of squares and the cubes is that instead of having perfect squares, we actually have perfect cubes. That's the difference. And so a to the 3rd is a perfect cube. Now again, you don't have to memorize this layout, but it does help a little bit. And so here's an acronym for you to use to help you memorize which signs go where. Because if you look, sum of cubes and difference of cubes are extremely similar, except for the sign location in the pattern. And so the word SOAP can help you remember what signs go where. So the first sign is the same. First sign is the same. The second sign is always opposite of the first one. And then the third sign is always positive. And that is because you have to take b and square it. That's why the second sign is always positive. And that's how you can use SOAP to help you remember which signs go where. Now, how do we find a and b? Well, if this is a to the third and I need a and b, well, that means a has to be the cube root of a to the third. That's why it's a perfect cube. Similarly for b, if this is b to the third and I need b, that means b has to be the cube root of b to the third. So same idea as difference of squares. It's just instead of working with squared numbers, we're working with cubed numbers. So let's look at example 3. Factor y to the third plus 512. So we're going to factor this with sum of cubes. Sum because there's a positive in the middle, and cube because y to the third and 512 are both perfect cubes. So let's see, this should be a to the third. So that means a needs to be the cube root of y to the third, which a cube root is what times itself 3 times gives you what's inside. So y times itself 3 times is y to the third. Now 512 should be b cubed. Well, that means b has to be the cube root of 512. So the cube root of 512 is 8. So these are both perfect cubes. So according to the pattern to factor sum of cubes, we're going to take a plus b, then a squared minus a times b plus b squared. So the first factor is a plus b. So a is a y, b is an 8, and add them together. The second factor takes first a squared. So a squared, so y and square it will be y squared. Let me put some parentheses around here. Then the minus, and then a times b. So we're going to take y times 8, which we can just write as 8y. Plus, then we're going to take b and square it. So 8 squared is equal to 64. And this is our factorization from sum of cubes. Find your a and your b value and then follow the pattern set up for sum of cubes. So for number 4, again, always try to see if you can divide out a common number or variable to make it a little bit simpler. So I know that both 250x to the fourth and 128x can be divided by a 2x. So I'm going to take the 2x out to the side, and we're left with 125x to the third plus 64. Now, hopefully these are both perfect cubes. I know x to the third is a perfect cube, so hopefully 125 is as well. So pause the video, try to factor out this piece using that sum of cubes pattern. And here's your factorization for number 4. Difference of cubes is the exact same process. The only difference is you have a minus inside of your cubes instead of a plus because it's a difference. So again, the sign stays the same. So same sign, opposite sign, always positive. So same pattern, just your signs are going to be changing placements. So let's look at number 5. So factor 54n to the 6th minus 2n to the 3rd. So the first thing we're going to do is we're going to divide out the common 2n to the 3rd that both of these terms share. So 2n to the 3rd factored out will leave us with 27n to the 3rd minus 1. Now we're going to use the sum or the difference of cubes. Hopefully this is going to be a difference of cubes. So a to the 3rd, so the a should be the cube root of 27n to the 3rd, which is a 3n, because 3 times 3 times 3 makes 27. This should be b to the 3rd, so b should be the cube root of 1, which is still a 1. 1s are kind of weird. So these are in fact both perfect cubes, so we're going to use the layout for difference of cubes, so a minus b times a squared plus ab plus b squared. And so if we put these in where they go, a is a 3n minus b, which is a 1, times a squared. Now, a is actually 3n. So when you take 3n and square it, you're squaring the 3 and you're squaring the n. So 3 squared makes 9 and n squared makes n squared. Plus a times b. So 3n times 1 is still 3n. Plus b squared, but if I take 1 and square it, I still get 1. Then we can't forget that we did pull out a 2n to the 3rd in the very beginning, so the 2n to the 3rd must drop down and follow us along as a factor. Pause the video, try number 6. And here's what you should have had for number 6. So that's these special cases of factoring. And so again, you will have these layouts, these formats, patterns available to you. You just need to know when and how to use them. Let's look at what happens if there's 3 terms, because if we look at our flowchart, we've talked about what happens with 2 terms. Well, what if there's 3 terms? Well, this is going to be factoring using the basic AC method. And so let's actually begin with number 8. We're going to do number 8 together, and then I want you guys to do number 7. So let's start with 8. So the first step on our flowchart is to find the greatest common factor. So the greatest common factor of 10 n to the 5th, 15 n to the 3rd, and negative 100 n is a 5n. I can divide all those numbers by 5, and I can divide them all by at least a single n. So we're going to have 5n to the side times 2n to the 4th plus 3n squared minus 20. Now when we look at our flowchart again, we count how many terms are left over here. And there are 3 terms left over. So according to our formula chart, if there are 3 terms left over, we're going to factor using that AC method. And we're going to use the middle exponent when we split apart b at the end. So the AC method says that we should multiply a and c together. So a times c gives us a negative 40, not x, sorry, negative 40n to the 4th. And we have to add up to be the middle term, which is 3n squared. So a little different because now we have some different variables and exponents here. But the process remains the same. We need to find 2 numbers that multiply to be negative 40n to the 4th and add to be a 3. So to multiply to a negative number, I know I need a negative number and a positive number. So negative 1n squared times 40n squared. I'm going to add those in my head. Negative 1 plus a 40 is not 3. So then we try negative 2n squared times 20n squared. If I add that together, I get 17. Not what I need. So then let's try the next one. 3 does not divide into 40, but I know 4 does. So negative 4n squared times 10n squared. Well, that adds up to be a 6. I'm getting closer. Negative 5 I can divide into 40. And if I add those together, negative 5n squared plus 8n squared, there's my 3n squared that I need. So these are the 2 numbers that b will split apart into. So we have the 5n hanging out. We have 2n to the 4th. Then we're going to split apart b. So b gets broken up into negative 5n squared plus 8n squared. And we need the square because remember, these should be like terms and they should add up back to be 3n squared, which is why we had to take the exponent of the middle one when we broke it apart. Now follow the same process we did back when we just had squares and not fourths. Divide this in half and take out the common number between 2n to the 4th and negative 5n squared. I can divide out n squared from both of those. So n squared times 2n squared minus 5. On the right-hand side, I can divide out a 4. So if I put plus 4, we get 2n squared minus 5. And just like before, the 5n follows, and these 2 inner factors should be the same. That creates one factor, and the other factor is created from n squared plus 4. And then we still have to make sure we're dropping the 5n down along with us. Before we say we're done, however, we need to check some things. So I now see that I went from 3 terms down to 2 terms. So I need to make sure that these don't factor any further. So if I look at my flowchart, if there are 2 terms and the exponent is even, so like a 2, I need to check for difference of squares. So let's see. I have 2 terms here. The exponent is a 2, and I do see a minus, so this could be difference. However, 2n squared is not a perfect square. There is no square root for 2, so this is not difference of squares. I cannot factor that any further. Let's check this one. So I have 2 terms, but there's no minus in the middle. So automatically, this is not difference of squares. So this is as far factored as this polynomial can go. I want you to pause the video and try number 7. Don't forget to take out a common factor first if possible. And here's your solution for example number 7. Now let's look at the final piece. So the final part of our flowchart is what happens if there are 4 terms. Well, 4 terms is called factoring by grouping. but you've already been doing factoring by grouping without even realizing it. Right here, where you took the 4 terms and you split them in half of 2 and 2, that is factoring by grouping. So really, you've been factoring by groupings for weeks now. We just need to, they've already done this part for us where they split apart the middle term. So we're starting here. So we're starting by splitting this in half and taking out common numbers from the first 2 and the last 2. So if you look at number 9, first look for a common number overall, but m to the third, m squared, 7m, and 7, there's no common number that I can divide out because I can't take an m because this one does not have an m, and I can't take a 7 because these two don't have 7s. So we have to do the factoring by grouping process because there are 4 terms, and according to my flow chart, if there are 4 terms, we factor by grouping. Well, we're going to group the first 2 together. So we're going to split this guy in half, and we're going to group the first 2. So the first 2 I can divide out m squared. So m squared times, we have m minus 1 left over. On the back 2, I can take out a 7, and we have m minus 1 left over. Then I see that the m minus 1s are the same, and we're left with m squared plus 7. But again, we need to make sure that we're done factoring. And so we look at what we have. This is no more, there's no exponents here, so that's probably done factoring. We need to check here and see if I can do anything else. So a 2-termed item with a even exponent. So 2 terms, even exponent, check for difference of squares. So we look, we have m squared plus 7. So since it's a plus, it can't be difference of squares. And so this is as far factored as this is going to go. Now let's look at number 9. So number 9 is a little more complicated. So we have 64 n to the 4th minus 192 n to the 3rd plus 27n minus 81. And so we need to figure out, there's nothing that divides into everything. There is no GCF to take out because I can divide these by 2, but not this one. I can divide these guys by 3, but not this guy. And this one does not have an n on it, so I can't even divide out n's. And so we're stuck with the numbers we have. So we're going to go ahead and do the factoring by grouping. We're going to split this guy in half, and we're going to look at the first 2 terms. Now, we want the greatest common factor of 64 and 192. So what I like to do is I like to start with a smaller number and see what is the highest number I can divide 64 by. Well, itself. The highest number I can divide by 64 is 64. So let's check and see. Does 192 divide evenly by 64? And yes, it does. We divide evenly by 3. So we can actually divide out a 64. Now, n to the 4th and n to the 3rd, I can take out n to the 3rd. So 64 n to the 3rd comes to the outside, and we have n minus 3 left over. Now let's look at the other half, 27n and 81. So again, 27n and 81, I'm going to try a 27 because that's the lowest number of the 2, and I know I can divide 27 by itself. So 81 divided by 27 is in fact a 3. So I can divide out a 27 from both of those numbers. And we're left with n minus 3. Now we see that, okay, n minus 3 and n minus 3 are the same. And we're left with 64n to the 3rd and 27. Now that we're done doing the factoring by grouping, let's check again. I have something with 2 terms but no exponent, so this is as low as it's going to go because there's no GCF between n and 3. But I do have this, and I have an exponent of a 3. So if I have 2 terms, let's look at our flow chart. 2 terms, exponent is a 3, check for sum or difference of cubes. So if these are perfect cubes, then I can use the sum and difference of cubes. So 64n to the 3rd is a perfect cube, and so is 27. And so what we can do is we can take this even further by using the sum of cubes. So let's go ahead and do that. So this should be a to the 3rd. So a is going to be the cube root of 64n to the 3rd. Well, the cube root of 64 is a 4, and the cube root of n to the 3rd is n. This one here should be the cube root of 27. So b is going to be plain old 3. And so now we're going to use our sum of cubes pattern. So a plus b times a squared minus ab plus b squared. So we have a, which is 4n, plus b, which is a 3, close parentheses, times a squared. So we're going to take 4n and square it. 4n squared. So that means 4 squared and n squared. So 16n squared minus, multiply a and b together. So 4n times 3 makes 12n. Plus b squared. Well, 3 squared makes 9. So there's the sum of cubes portion. We still can't forget about this n minus 3, though, that we had from the beginning. Now, we do see a square here. There is something with 3 terms and squared. Normally, we can factor that out. But because this resulted from sum of cubes, there's nothing we can do with this. 16 times 9, there's nothing that multiplies to that number, 144, but also adds to 12. So this does not factor any further because it came from sum of cubes. This one is complete the way it is. So this is our final factored form for example number 9. I want you to pause the video and try to find this next example in the furthest factored form possible. And here's your result for the final example. Make sure you don't stop here. X squared minus 4 can be factored further using difference of squares, and x to the third minus 1 can be factored further using difference of cubes. Keep this flowchart handy. This flowchart will be very helpful in learning how to factor polynomials.